Hi, my name is Nandini Krishnaswamy, and I'm a postgraduate student at Columbia University and a research affiliate at Lawrence Berkeley National Lab. At LBNL, I am part of the Daphne team, where we work on research related to deep and autonomic high-performance networks. The paper I will be presenting is Data-Driven Learning to Predict Wide Area Network Traffic, where we developed LSTM techniques to forecast network traffic growth, specifically for wide area networks. So why is this a relevant problem? In recent times, wide area network traffic service providers are witnessing extreme traffic growth. Traffic is growing at exponential rates while underlying hardware is also too expensive to upgrade. For example, in internet traffic, there have been surges of video streaming and mobile applications. As another example, ESNet, which is the Department of Energy's dedicated science network, is projected to experience 62% traffic growth every year. This extreme traffic growth threatens to lead to congestion in links, which could lead to slow speeds and packet loss. So this diagram illustrates the growth rate of traffic on ESNet backbone. As you can see, there's a projected 62% traffic growth every year. Since this is a very costly issue, network operators take expensive measures to avoid it. Specifically, they usually provision available network bandwidth to 40% utilization in case there's a sudden traffic surge during transfers. This means that the vast majority of network bandwidth is going to waste. Especially as demand grows, capping utilization like this becomes an unscalable solution. So our work tackles this unique problem by proposing statistical and deep learning methods to predict traffic surges multiple hours ahead, thereby helping to prevent bottlenecks and improve network utilization. So there are several formidable challenges posed by the task of predicting network traffic. For one, traffic is noisy and exhibits pseudo-random behavior. Another challenge is missing data. Interfaces sometimes miss logging traffic and will therefore populate the data with null values. The third challenge is performing multiple hour forecasts, as most time series algorithms are designed to predict only one step ahead. Predicting multiple steps results in an error buildup as the prediction goes further into the future. The final main challenge is the task of unsupervised machine learning. Since time series methods such as ARIMA and Holt-Winters require global parameters to be set in advance, they're not necessarily scalable to different traffic scenarios. Therefore, unsupervised machine learning is better suited to learning hidden patterns from data. Our data sets are comprised of simple network management protocol data with traffic recorded in gigabytes at 30-second intervals. We use real network traces, specifically 4 transatlantic bidirectional traffic traces, 8 in total, as you can see, collected from a global research wide area network that connects labs in America and Europe. The data is collected over the span of 1 year, and we aggregate the traffic data to 1 hour intervals for the purpose of reducing the prediction model complexity. Aggregation compounds the burst patterns and does not affect the accuracy of the predictions. The first 88 days of data are used for training. The 89th day, at hourly granularity, is set aside as validation data, so 24 hours. And the 90th day is set aside as test data. The first component of our methodology involved performing Fourier analysis to extract frequency patterns across traffic traces. The purpose of this was to validate that there was variability between the traces used in the study. The following heat map shows the correlation between all possible pairs of links during different months in 2018. So blue illustrates low correlation, and then red illustrates high correlation. So some links may be correlated as a result of sharing common traffic paths. The links we chose, you can look at one example, London, New York out, and Amsterdam, Boston. As you can see, the links we chose tend to exhibit low correlation across this year. So this, the purpose of this was to validate why we are using these links. So after confirming that the set of traffic traces exhibited variability, we applied several different prediction methods to forecast future traffic, using root mean square error as the metric to assess model performance. Our algorithms are implemented in Python, and we use TensorFlow for the deep learning methods. We use two classical time series models as baselines for performance. These two models are ARIMA and Holt-Winters. ARIMA uses autoregressive moving averages to predict future points. Tuning ARIMA requires setting parameters for lag order, degree of differencing, and the size of the moving average window. Setting parameters for ARIMA involves inspecting the partial autocorrelation plots of the data. Holt-Winters is triple exponential smoothing, and the smoothing equations are for level, trend, and seasonality. Parameters for Holt-Winters are tuned using trial and error or grid search. Time series algorithms such as ARIMA and Holt-Winters are bolstered by adding seasonal patterns as model features, but this process is error-prone. Hence, we turn to deep learning to learn features from the data. We built several variants of LSTM networks. An LSTM is a type of artificial recurrent neural network architecture, which is different from a feed-forward neural network in that it contains feedback loops to connect past decisions to future predictions. This quality of RNNs makes them well suited to process sequences of data. However, traditional RNNs suffer from the vanishing gradient problem. And what this means is that during backpropagations, the gradients calculated are very small. So this prevents weight updates and kind of stops the network from training. So how do we overcome this problem? LSTMs overcome this problem by using a special memory block that stores temporal state using gates for allowable information. By controlling information flow at every step, LSTMs are able to learn long-term dependencies. There are three variants of LSTMs that we used. The upper left diagram here shows the architecture for a simple LSTM with just one LSTM layer. This model uses past time series data to learn the traffic pattern between inputs. The next diagram here differs from the first by the addition of one LSTM layer. So literature has shown that increasing the number of hidden layers can improve the accuracy of the model, but sometimes this also leads to overfitting. The final diagram shows the sequence-to-sequence model architecture. This learning method has two main components, an encoder and a decoder layer. The encoder LSTM layer learns behavior representation from the input sequence and generates a fixed size context vector, which is also known as the learned vector. This context vector captures features and uses these to project the decoder output, which is also represented by another LSTM layer. The context vector can be used to project future data behaviors. Now I will go over the details of our experiment. So to select the parameters for the ARIMA model, we inspected the traffic data plots and their corresponding autocorrelation and partial autocorrelation plots. These plots indicated that the series for each of the selected link traces is stationary, so the model did not require differencing. Furthermore, the plots also indicate that the series is not over-differenced, so the model did not require an MA term. To account for the possibility of under-differencing, we added one AR term to the model. The Holt-Winters model coefficients correspond to their respective smoothing equations. Tuned using trial and error for 10 epochs, we settled on coefficients of 0.7, 0.2, and 0.9, respectively for level, trend, and seasonality. When building the LSTM models, we tested the model with 10, 24, and 50 nodes in the hidden layer, but we found that the performance didn't vary much with respect to the number of nodes. So we just used 24 nodes as a standard across all the models in the comparison. We also tested various activation functions and found that the tan H yields the lowest MSE. For LSTM training, we use the Atom Optimizer with default parameters. Each model was trained for 10 epochs and run 3 times each to average the results. So model performance tends to differ depending on the link, but the LSTM models tend to show considerably lower RMSE across the transatlantic links. The exceptions include the AOFA London inbound and the Washington CERN inbound, which this may be explained by the strong presence of seasonality or faulty data collection. So the first table displayed here illustrates the RMSE of each of the models on the respective links. The stacked LSTM is the lowest error model for 3 of the links. Holt Winters is the lowest error model for 2 links. And the simple LSTM is the lowest error model for 2 links as well. The table below illustrates the performance of the LSTM models in reference to the classical time series models. So on average, the predictions are improved by 70% or more with the LSTM models. Our paper findings have a number of implications for the network prediction research and engineering communities. These results validate the usefulness of deploying prediction tools with traffic monitoring tools and could have an immediate effect on network utilization. Currently, our methods are being optimized for next 24-hour prediction, but there is potential for further research to extend the prediction periods. Additionally, experimenting with advanced neural network architectures could help improve the accuracy. Thank you for attending my presentation, and I will be around to answer questions.